Okay, this is going to be the first video on section 6.6 looking at surface integrals. So a reminder of parametric curves. So a plane curve, for example, if we have r of t is equal to x of ti plus y of tj, so a vector valued function. And then t is going to be your parameter. An example of a plane curve would be r of t is equal to cosine ti plus sine tj. And so that's just your unit circle with an orientation of counterclockwise. Okay. We can have a space curve. R of t is equal to x of ti plus y of tj plus z of tk. An example of this would be r of ti plus sine of tj plus tk. So be a helix or a spring. So it's going to have the circle characteristic to it, and then as the t increases, the spring goes up higher and higher. We need a second variable or parameter if we want to generate a surface. So here we just kind of have like a wireframe. So if we want to fill things in, we need a second parameter. So parametric surface, let x, y, and z be functions of u and v that are continuous on a domain D in the UV plane. The set of points x, y, z given by r of uv is equal to x of uvi plus y of uvj plus z of uvk. That's a parametric surface, and then your parametric equations would be x is equal to x of uv, y is equal to y of uv, and z is equal to z of uv. And so we're going to take a couple examples that are in parametric form, and then we're going to convert them into rectangular form. So number one there we have r of uv is equal to ui plus vj plus uvk. So what we can do is we can go ahead and say that x is u, y is v, and z is uv. So then make the replacement of u and v for x and y respectively, then we have z is equal to xy. Okay, and now why we might want to do this to get a better idea of what the graph looks like is if we're going to try to sketch these, kind of get an idea what you're going to look at. You're going to be plotting a lot of different points. The book mentions, you hold the u fixed and you let the v vary, and you let the v be fixed and then let the u vary, and that'll kind of get you an idea of what the shape is. So converting it back to rectangular can help with identifying what shape you're looking at. Okay, so if we look at the second one, we have r of uv is equal to u cosine vi plus u sine vj plus uk. So here our x is equal to u cosine v, y is equal to u sine v, and z is equal to u. If we use the x squared plus y squared, that's going to get the Pythagorean identity here. So u squared cosine squared v plus u squared sine squared v. It's going to be equal to u squared times cosine squared v plus sine squared v, which is your Pythagorean identity, and that's just going to be 1. So this is going to be u squared times 1. So then x squared plus y squared is equal to u squared, which u is equal to z. So we have x squared plus y squared is equal to z squared. And that's a cone, and that's going to open up along the z-axis. Okay? All right, let's do a couple more. Okay, so next example, r of uv is equal to 2 cosine v cosine ui plus 2 cosine v sine uj plus 2 sine vk. And so this kind of looks like spherical coordinates in some sense, but with the z on spherical coordinates, it would be rho cosine of phi instead of rho sine of phi, but it's going to be similar. So x is equal to 2 cosine v cosine u, y is equal to 2 cosine v sine u, and z is equal to 2 sine of v. So it is going to end up being another parameterization for a sphere. So let's go ahead and take a look at what x squared plus y squared plus z squared is going to look like. So it's going to be 4 cosine squared v cosine squared u plus 4 cosine squared v sine squared u plus 4 sine squared v. Okay. Now the first two terms we can factor out a 4 cosine squared of v, and what we're left with is cosine squared u plus sine squared u, and that's going to be your Pythagorean identity, which is going to all absorb to 1, that being the cosine squared u plus sine squared u. Okay, and then we still have the plus 4 sine squared of v at the end there. Okay, so now we have 4 and then cosine squared v plus 4 sine squared v. This is going to be equal to 4 times the quantity cosine squared v plus sine squared v, and that's going to be equal to 1, your Pythagorean identity again. Okay, so we have x squared plus y squared plus z squared is equal to 4. So it's not quite spherical coordinate system, but it's a similar parameterization here. Okay, all right. So we got a sphere. All right. And number 4 here we have r of uv is equal to 4 cosine ui plus 4 sine of uj plus vk. So our x is going to be 4 cosine of u. Our y is going to be 4 sine of u. And our z is equal to v. So if we look at just the x squared plus the y squared, that's going to be 16 cosine squared of u plus 16 sine squared of u. Okay. So that's just going to be equal to 16 using the Pythagorean identity. So you have x squared plus y squared is equal to 16, which is a cylinder. Z is not related in this, so it's going to be free to be whatever we want. But x squared plus y squared equals 16 is going to be a circle, and since the z is free to be whatever we want, then we actually have a cylinder. Okay, so this is taking parameterizations, vector value function parameterizations, and converting them into rectangular form. Now we're going to take stuff in rectangular form and come up with a vector valued function and a parameterization. All right. So it says find a vector valued function whose graph is the indicated surface. Okay, so we have a plane x plus y plus z is equal to 6. There's a variety of different ways you can do this. So simply we can let x equal u, y equal v, then u plus v plus z is equal to 6. So z is equal to 6 minus u minus v. So r of uv for a vector value function is going to be ui plus vj plus 6 minus u minus v, and that'll be our k component. Okay, so we parameterize the plane there. Okay, for part 6 here, z is equal to x squared plus y squared, and then that part that lives inside the cylinder x squared plus y squared is equal to 25. So we have a paraboloid, z equals x squared plus y squared, and then a cylinder x squared plus y squared is equal to 25. So we'll go ahead and draw a little bit of that. So first we'll draw our circle. Well, I'm going to just draw what's in the first octant here. Okay, so there's your cylinder. And then we have our paraboloid. It's going to look something like that. Okay. And so we want to parameterize just the paraboloid contained within the cylinder here, assuming that the z is greater than 0. We're not looking about the. Oh no, we're not looking at a cone. Sorry, it's a paraboloid. So yeah, we're not going below the xy plane. Okay. So what we'll do is we'll let x equal u cosine of v and y equal u sine of v. And so our paraboloid is going to be, we got circles in here of varying radii, and so for our parameterization, we're going to say that our radius is going to be u. So we're going to let the radius vary, and we want it to vary between 0 and 5. 5 is going to be the absolute largest there once it hits the edge of the cylinder. Okay. And then the v, we just want that to vary from 0 to 2 pi, so you get those full complete circles. Okay, and then z, we'll get to in a minute here, x squared plus y squared is equal to u squared cosine squared v plus u squared sine squared v. So we have it equal to u squared, and what we can do is we can say, all right, well let's let this. Oops. So we have u squared is equal to z squared, so that'll give us our parameterization. Z is equal to u. No, it's sorry guys. We're making a substitution here, so this would be not z squared, it would just be z. You have it, the paraboloid is z is equal to x squared plus y squared, so z is equal to u squared. Okay, there we go. All right, the last thing we're going to take a look at is the normal vectors and tangent planes. Okay, so normal vectors and tangent planes. Let S be a surface with parameterization of R of uv is equal to x of uvi plus y of uvj plus z of uvk on the domain D, okay, in the uv plane. And so what we can do is we can divide up this domain D into a bunch of little squares or rectangles, and the squares will have a width of delta U and a height of delta V, okay? And then that little square or rectangle in domain D is going to be mapped to the surface, and so it's going to become a tile. So you can kind of see it here. This is going to be from the OpenStax calculus book. It's going to be in the section 6.6 if you want to look at a little bit clearer pictures there. And then we get our tangent vectors, okay? So your tangent in the direction of V and tangent in the direction of U at a point P on this little piece of tile there. So your tangent vectors, T of U is going to be the partial of x with respect to U, of uvi plus partial of y with respect to u uvj and partial of z with respect to u uvk. Your partial derivative with respect to v, t sub v, or I think your book also you use also r of v and r of u. Okay. T of v or r of v is going to be the partial of x with respect to v, uvi, partial of y with respect to v, uvj, plus partial of z, uvk. Now, if we pick a particular point, p naught being a point u naught comma v naught, or we'll just call it p, and if we hold u naught and let v vary, then r of u naught v is going to be this part of the wireframe. Okay, and then if we take the derivative at that particular point, then we get our tangent vector with respect to v. Okay. And then we do the same thing, we hold fixed v naught, Okay, and so then we get the other piece of your wire frame here, and then we can find the tangent with respect to V there. Okay. All right. Now, if we want to find the normal vector, we would simply take the cross product of T sub V and T sub U, or I think in the videos, and they might use R of U and R of V instead. Okay, here they're just using T for tangent. Okay. Now, once you have the normal vector n, we'll call it ABC, and a point x naught, y naught, z naught, recall that the equation of the tangent plane is a times the quantity x minus x naught plus b times the quantity y minus y naught plus c times the quantity z minus z dot, and that's going to be equal to 0. Recall the area of a parallelogram with adjacent vectors u and v is the magnitude of the cross product. So we have our tile down here, okay, and so our parallelogram here is an approximation of the actual tile, S of ij, on the actual surface, and so the sides of this parallelogram have length of t sub v delta v and t sub u delta u. So the area of that parallelogram, which is approximation of one of the tiles, is going to be the magnitude of T sub v delta v cross T sub u delta u. Using the property that a constant times the cross product of u and v is the same thing as the constant times vector u, and then cross with v is equal to the u cross with cv. That allows us to shuffle the constants delta v and delta u. We can shuffle them, and then using another property of magnitude, they'll be able to be shuffled out of the magnitude. And so the area of our tile here is going to be the magnitude of the cross product of T sub v cross T sub u, delta v delta u. Summing these all up, delta v and letting delta v and delta u go to 0, and using our book's notation, r sub u, which is the tangents in the direction of u, r sub u equals tangent the T sub u, and r sub v is equal to T sub v. Our surface area formula is going to be adding up all these tiles and letting the delta v and the delta u go to 0. Then you're going to get better and better approximation here. So your surface area is going to be a double integral over the region D of the magnitude of the cross product of r sub u cross r sub v. And then your book might use T sub u and T sub v instead. And so we're going to go ahead and use this surface area formula in the next video. So stay tuned for the next video.